G'day viewers. In this segment we'll talk about randomized multiple access control protocols. Okay, so that's a mouthful of a phrase, randomized multiple access control. But the topic is a fundamental one and also an important one in computer networking. The issue is simply this. We have multiple nodes, a set of nodes, who want to share a link. How do they do it? When they have traffic to send, who gets to send when? This is a scenario that comes up in Wi-Fi, for example, when you might have multiple laptops and they would all like to talk to the one access point. How do they decide who gets to send when? We've looked previously at multiplexing schemes called TDM and FDM, which divide up the link in terms of either time or frequency. They're well suited for continuous traffic, but not very well suited for computer networking where the traffic is bursty. So in this segment we're going to start looking at alternatives. To do that we'll use the simple model that's shown here, where we have the multiple computers just all attached to a single wire. So if we wire them together they can all talk over that wire, and we have the multiple access problem of deciding who gets to use the wire when. Now, like many networking issues, protocols, this actually turns out to be quite a subtle issue in many ways. The designs you come up with can have strange effects, strange side effects. One of the key things which makes this hard is that it is a distributed system. All of the different nodes there get to see what they can see locally attached to the wire, so they can send and receive messages to other nodes, but they have no overall view of what's going on in the system. So there's no one in charge, there's no special party. If there's someone in charge, like you or I, and we can look at this network and see what's where, we can organize things fairly easily. But we're now trying to solve a multiple access control protocol without that central view. That's what's difficult. Okay, so the schemes we'll explore are a family of randomized multiple access control protocols. What does this mean? It simply means that they use randomization to handle some of the difficulties like collisions when multiple nodes try and send at once. Randomization, or randomized multiple access control protocols, are the basis for classic Ethernet. This is one of the most successful networking technologies of all time that we'll learn about. And before we dive into it, I'll remind you the central problem here, which is that we want sharing while the data traffic is bursty. In this figure, for instance, these nodes, the middle one looks like it's asleep. The one on the right is maybe occasionally sending a bit of traffic, but not much. The one on the left is very busy. If we use TDM or FDM to divide the link up into three different parts, the one on the left would only get a third of it, the other ones aren't really using their share. What we would like to do is statistically multiplex these demands so that the one on the left could use most of the wire while the middle one's asleep and the right one's not using it much. So let's see how that works. Well, our story for randomized multiple access control protocols actually begins in the Hawaiian Islands in the late 1960s. In this setting, a new kind of way of multiplexing a link was developed. Rather than use TDM or FDM, this new protocol was devised by a guy called Norm Abramson. The setting here was that we have all of these different islands, Hawaiian Islands. They have a wireless link. The islands want to send to one another. They're distributed. How do they decide who gets to send when? And let's not use simple TDM and FDM. Here's the protocol. Like many things, it's a very simple idea. It works like this, the Aloha protocol. When a node has traffic to send, guess what? It just tries to send. If you send successfully, you're going to end up getting an acknowledgement back of some form. I won't go into all of the details here, and then that means everything's okay, it was received. If you don't get an ACK, that means there's been some collision, maybe two nodes have tried to send at once. So all you do is you wait a random amount of time and try again. That's it, a very simple protocol. What could possibly go wrong? Here's how it works. Just as a bit of a diagram, you can see we have 5 different users here, and they're all sending packets over time. If we follow the protocol, they'll all just send when they have traffic to send. Now, if more than one of them sends at the same time, the signals will superimpose. We won't be able to receive it correctly. There's a collision and it's lost. So you can see here, several packets are involved in a collision over this time window. some portion of the packets were being transmitted at the same time, and also over here. However, even though some of these frames are lost, many of the other frames get through. Okay, so is this a good idea or a bad idea? You can think about that for a minute, and I'll tell you the answer. Actually, it's a pretty good idea on the whole, or at least a reasonable one. It's a dead simple scheme. It's fully decentralized. There's no central point of control here that can fail or is required for the system. And it works quite well under circumstances of low load where the link is not busy most of the time. Now, for many networks, low load is actually a common case. We might have many computers, but often they're really not doing anything much with the network, or at least they used to before we have all of these background processes. Under low load, well, if the network's mostly not being used and someone has a packet to send, they can just go for it. It works. So it's relatively effective under low load. Of course, the problem is when you really want to use it and multiple people want to send, which was basically our problem, it's not efficient then. You'll get collisions. You can actually do some sort of randomized analyses of this, and if you dived into all of the details, you'd find that the most efficiency you could get in terms of the fraction of the link that's successfully used to transfer packets tops out at about 18%. So we've wasted more than 3/4, more than 4/5 of this link, its capacity. That's not so good. You can actually come up with some improvements here. If you slot time so all packets begin on regular boundaries, it turns out that you can double the efficiency from 18 to 36%. And the reason for that is now collisions are all or none. You no longer have a packet or a frame that's mostly mated, and then at the very end someone just clips the end of it and the whole thing is ruined. But rather than look at that, we're going to look at other kinds of improvements to turn this into a much more effective protocol. And the place that I want to get to is so that you understand the design of something called classic Ethernet. Ethernet was invented by Bob Metcalfe in in 73, the early 70s here. It became really the most popular LAN, local area network technology of all time. So in the 80s and 90s, it was very common to see Ethernets deployed in buildings. And it worked like this. Essentially, all of the different computers here were wired to the one cable, which snaked around the building and connected all of these together. It was, usually a 10 megabit per second cable, somewhere near the beginning. All the nodes really have to do is solve the multiple access control problem, and then they can all talk to one another. So to do that, we're going to improve on aloha in several ways. Let's look at those improvements. The first way that Ethernet improves upon aloha is with a technique called CSMA, for Carrier Sense Multiple Access. This simply means that a node should listen to the medium to see if it's busy before it sends its frame. It sounds like rather an obvious technique, but it's not quite so obvious in the sense that it's easy to engineer with wires, and so Ethernet does it in a wired context, but it's actually more involved in the case of wireless, as we'll get to in a subsequent lecture. Okay, so our technique is now simply to listen before we send packets. And the question I have for you is whether this is in fact going to eliminate collisions completely. Let's think about it for a minute. If every node listens before it sends, will this eliminate collisions? Why or why not? Well, actually, it doesn't eliminate collisions completely. Now, many people, when posed with that question, will say, well, it's still possible if two nodes send instantaneously to have a collision, if they send at the same instant. However, even if they send at slightly different times, a collision is possible. And the reason for this, the intuition, is that it takes time for these frames to propagate along the medium. So, for instance, here's what could happen. Well, actually, it's possible for both of these nodes. Here's one on the left. We have our 3 nodes in a network. This node to listen. Let's see, is there anything here? No, and start sending a frame. At the same instant in time, this node can listen. Is there anything here? No, and start sending a frame. Now, this can happen because it takes a finite amount of time for the frames to propagate from one end to the other and cause a collision. In fact, that time to propagate is d, our delay. Here's a picture of that. once again, just the two nodes, both sit as idle, both send, there will be a collision, it just hasn't happened yet. So it turns out that what we're really saying here is, do you remember the bandwidth delay product, which is a measure of how much information can fit on the network? CSMA, Carrier Sense Multiple Access, is a good defense against collisions only when this bandwidth delay product is small. And by small, I mean less than 1 packet. Much less than 1 packet. If that's the case, well, if there's much more than 1 packet, you can see in this picture the kind of thing that can happen. Someone can send, their packet can be on the medium, a collision will happen much later. If it's much larger than 1 packet, you're still sending, and your packet time is sufficiently long that the interval during which a collision can happen is small relative to a packet time. So collisions are less likely or less damaging because they only occur during a smaller window of time. The second improvement that Ethernet uses on top of LoHa is to use collision detection. Not only do we listen before we send or talk, but if someone else is talking or using the medium at the same time, then we stop sending. We detect that there's been a collision and we abort our own collision. In Ethernet, the way you abort a collision is you send a jam signal just to say to everyone, whoa, stop, there was a problem, and then you can cease transmitting your frame. Now again, this sounds like a fairly easy technique. It works well enough with wires. It's a little harder in the wireless context. So here in our picture, both nodes have detected a collision and they're both going to issue a jam signal. It's actually a little more complicated than I've been making out. When there is a collision, you would like all nodes that are involved in the collision to realize that a collision has occurred. Otherwise, a node could send its frame, think that everything is fine, and not realize that the frame never got there because of a collision. If there is one and all nodes know, then they can take action in the future, such as retransmitting their frame. So this leads us to think about how every node is going to realize that a collision has happened. And again, a key factor here is the propagation delay of the medium. There is a window of time during which a node can detect a collision. You would hope that if you send and someone else is sending, you know right away, but because of the propagation delay, it can take a finite amount of time. Here's a scenario. This node starts sending. Its signal propagates down to the other end of the wire. Now that takes about d seconds. Well, just before the signal gets here, this other node decides to send a packet, just an epsilon before. It starts sending and immediately it's going to detect a collision, but its signal is going to take, you guessed it, another d seconds to return to the other end. And it's only when it returns to the other end that this node here will see that there's another signal on the wire and detect a collision. That's then taken up to 2d seconds to detect a collision. In Ethernet, or with CSMA-CD, the technique that's used to detect collisions, we ensure that all nodes know that a collision has occurred by imposing a minimum frame time. We require nodes to send frames so that the minimum frame takes at least 2d seconds to send. That way, you'll still be sending the frame for the time interval during which you could detect a collision. So if there was going to be one, you'll know that a collision occurred. The node can't finish before the collision is what it says here, which is a good way to put it. If you do the math for an Ethernet, depending on the bit rate and the maximum length and hence the D, the amount of time things can propagate, you can work out that the minimum frame for an Ethernet is 64 bytes. This means that actually if you wanted to send a packet with a 1 character in it or a short message like OK, the minimum message size that you're going to send is 64 bytes regardless. If you try to send something smaller, it will be padded out. And finally, there's a third issue in Ethernet as we move away from Aloha, and that's the issue of persistence. This is a good illustration actually that these protocols, simply random access protocols where you just send, conceptually they sound very simple, but there can be very complicated interactions between different nodes when everyone independently follows all of these rules. Persistence is one illustration of that. So the persistence issue is simply the question of what one node should do if it senses that another node is using the medium. Obviously it's going to wait and not send right away, or that would cause a collision. But how long should it wait? That's the question. So what do we do now? Okay, well I have a brilliant idea. The node here on the left should simply wait until the other node is finished and then go for it. That's the simplest solution I can come up with. I like simple. Generally, we like simple designs. They're better. Sounds good. What could possibly go wrong? Well, as you might have guessed, something can go wrong. Here's the problem that you get if you use that scheme where you node that senses the medium busy, waits for that sender, and then sends immediately. Actually, that is a good design if you are the only node that is waiting on the medium for someone else to finish, because then you go right away. But what if there are 2 or 3 or 4 different nodes, all of whom wanted to send, and they're waiting for another node to finish? If they send immediately, they will all collide. In fact, we've really created a problem here with this rule of wait till someone finishes and then go for it, in that the node that's sending is almost acting as a perfect synchronizer for the other nodes. It's lining up all of their transmissions so that a collision is guaranteed if there's more than one of them. This is not good. It's also more of a problem with more load, because the more load, the more likely it is that more than one node will be waiting to send, so that you will get collisions. And the more collisions there are, the more nodes will have to resend their frames to try and get them through. So we'd like to do something about this. Well, if we shouldn't send right away, how quickly should a node send? The difficulty here is that it depends on the number of queued senders. If there is only one sender that's queued up and waiting to send, it should send right away. If there are 2 senders, you would like each of them to send with probability about a half, so that on average only one of them would go right away and the other one would wait. That would be good. On the other hand, if there are 10 senders, you would like each of them to send with probability about 1 in 10. We would expect that way that only one of them is likely to go. That way we'll make sure the network's used. But there's unlikely to be a collision, which will waste that bandwidth. In general, if there are n queued senders, then you'd want each to send with a probability of 1 on n. That's what we would like to happen. But since this is a distributed system and the load is changing dynamically over time, this node, or any of these nodes here, does not know what n is. What is n? If you knew what it was, you'd be able to send with probability 1 on n. But at any given time, a node doesn't know what n is. Well, there's a clever heuristic which is used in Ethernet to solve this problem. It's called binary exponential backoff, and it's a technique that's probably useful in a lot of other contexts where you're trying to adapt to a certain level of load. Binary exponential backoff cleverly estimates the 1 in n probability. And it does this by starting and optimistically assuming, after a collision, that, well, since there were a collision, at least 2 people were involved, but it will assume there was only 2 of you. And so every node that's going through this process will say, okay, I will wait only 0 or 1 frame times. That's 2 options. So I'm going to send right away with a roughly probability of half is roughly what it corresponds to. Not exactly, but roughly. If you collide again, you say, well, whoops, maybe there were actually more than 2 of us. I'm going to try again. This time, I will send my retransmission chosen randomly over a 4-slot time. So that's like sending with probability 1 on a quarter for every time slot, roughly. If you collide again, you say, wow, well, maybe there are actually more than 4 of us. I'm going to double the number of slots I'm going to wait for. That's 8 slots now. I'll send with probability 1 on 8, roughly. And so on. So what binary exponential backoff is doing is it's doubling the interval for which you're waiting over with each successive collision. Now, as you know, this exponential growth and doubling gets quickly very rapidly. So even if you needed to wait for, if 100 nodes were contending all at once, binary exponential backoff will get you there relatively quickly. All you would need to go through is, 6 or so different collisions, 6 or 7 different collisions, and you'll get up there fairly quickly. So in practice, binary exponential backoff is very efficient. It's able to adapt over a large different operating range. And this is a property we very much like to see in our network protocols. You'll often hear the word scalability in networking. We would like to design network protocols which work when the number of nodes in the network is very small, but they also work well when the number of nodes in the network is very large. That way, as our network grows, there should be no problem. Binary exponential backoff works well when there are very few nodes, because it optimistically starts by assuming that there's no one much around and you can send rapidly. But it also works well if there are a large number of nodes, because by doubling this backoff, it very quickly gets to about the right operating point. Okay, so when you put all of these improvements together, we have classic Ethernet. Recall classic Ethernet was this hugely popular LAN technology for connecting computers. This shared cable snaked around the building, you connected the computers to it, they could all talk. There's some details here just to relate to our physical layer talk. It was a 10 megabit per second cable, it's a coaxial cable. The signals were sent here using baseband signaling. Now, the key for Ethernet is this multiple access control problem. And the solution that Ethernet uses is one persistent CSMA CD with BEB. Wow, that's a mouthful. But we've seen everything that you need to understand this. So Ethernet uses carrier sense multiple access. That's this bit where you listen before you talk. And it further uses collision detection so that if two people start sending at once, they realize there's a collision and stop so that we don't lose too much efficiency. The stations, the nodes using the Ethernet are persistent. They're what's called one persistent, meaning that if someone else is sending, they wait for a moment and then they send right away. They try and send right away. Well, we know that can cause collisions if people queue up, so Ethernet also includes binary exponential backoff to adapt the persistence so that everything works. And there we have this technology. I'll tell you just a little bit more about it. And to do that, what we'll do is we'll look at the structure of frames that are sent across the network. It's often very helpful for protocols to look at the format of their messages, because we can see the different functions that are included, the different information that's in these messages, and that helps us understand the different functions of the protocol. One thing that you'll immediately see if you look at an Ethernet frame that we haven't talked about before is it has addresses on it, a source and a destination address. We didn't need this when we were talking about a link where a sender is connected to a receiver, because whatever was sent, it just went down to the other end. For our multiple access scenario, we do need this because there might be several laptops around an AP. If there is a frame in the air, who's it for and who did it come from? Ethernet includes this kind of addressing. The destination address actually goes first here. That's the first thing that is sent out, because remember here to the left this is what is transmitted first. So this means the destination address comes first. Everyone can look at it and see if the packet, the frame I should say, is destined for them. There is a whole frame format here. We can see some of our framing concepts. What we learned before really is useful. The frame begins with a preamble here to identify it. That's actually a bit of a signal from the physical layer to help with our framing problem. The frame ends here with what's called a checksum. This is used in a generic way. The checksum is actually this CRC32, or a 32 bits cyclic redundancy check. So that's a check that's used for error detection. If you remember all of that, that will allow us to work out if something's gone wrong. Now, interestingly here, there are no acknowledgements or retransmissions. Ethernet, because it's sent over a wire, is usually fairly reliable. The CRC is just there in case something goes wrong to weed out errors, but mostly there won't be any errors. If there are errors, this means since they're not handled by Ethernet, other than collisions, that is something that might be thought of as an error that is repaired by Ethernet. But anything else that's caught by the CRC, well, that will just have to be handled by the higher layers. And we'll see some of that much later. Okay, and before we wrap up on Ethernet, there's one important thing that I want to remind you about. And that is we've just looked at classic Ethernet. Now, it turns out that modern Ethernet, the kind of Ethernet that you'll see in any building today, does not use this multiple access control protocol. It's really based on switches. That's these boxes here. So there is a twisted pair, for instance, cable that connects every different computer to a different port on the switch. And the connectivity is happening inside this switch. This is called switched Ethernet or modern Ethernet. The difficulty is that everyone will call both of these things, they're all just Ethernet, which can be very confusing. But again, we've studied classic Ethernet, which is how the Ethernet evolved and is all about multiple access control. Ethernet, as you'll find it in buildings today, is this switched form of Ethernet that we'll look at a little later.